Good afternoon, folks. How are you today? Welcome to spring semester at RIT. This is MECE 317 Numerical Methods class. My name is Vinnie Gupta. I'm a professor of mechanical engineering. I have been teaching at RIT for almost 40 years. I have taught this course, Numerical Methods, 20 or 25 years or so. Since this course is online this semester, the best way to contact me is through email. I check my email frequently throughout the day so I can respond to you fairly quickly. I don't have office hours like in-person office hours, but I'll be very happy to meet with you and have a face-to-face conversation using Zoom. Send me an email and we can set up an appointment. All the materials that you are seeing here, this video, these slides, everything is on my courses. So log into my courses and go to this course page and you will find all these materials. I have a lab teaching assistant, Anthony Lord. His email is listed here. He is going to maintain an office hour during the lab time on Fridays. So you can contact him through Zoom and seek help. So contact the TA if you have any questions about lab or lab report. But if you have any questions about your lab grading, email both the TA and me, so I am in the loop. For all other questions not concerned with labs, you can directly email me about instructional materials, quizzes. If you need any clarifications, I can always meet with you face to face in Zoom, or we could correspond through email. The objective of the course, this course is going to focus on numerical methods to solve a system means one or more linear or nonlinear equations. You will learn curve fitting, you will learn how to evaluate a definite integral, you will learn how to evaluate derivatives of a function. You will learn how to solve a system of ordinary differential equations, also called initial value problems. You will learn how to solve a second order ordinary differential equation, also called boundary value problem. Now, many people ask me about prerequisites for the course. The only prerequisite for the course is DiffyQ. So if you have not taken linear algebra, there is no problem. If you have not taken a boundary value problem course, there is no problem. I am going to start from the very basics. If you have taken the course, I hope you will appreciate and gain a better insight into what you learned in those courses. We will also learn some numerical analysis to understand errors, error bounds, convergence properties of a method, and relative stability of a method. So after you have finished the course, you should be able to identify, given a mathematical problem, does it belong in any one of the above 6 groups? So I have these 6 bullets here, and you should be able to say, given a problem, is it in those 6 groups? If it is, you should be able to name numerical methods that can solve that problem. Then you should be able to select an appropriate numerical method and implement it using Excel with VBA, Visual Basic for applications. There is no textbook for this course, required textbook, but if you really want to have a textbook, you can go to the library or buy it online. This book, Numerical Methods for Engineers by Chapra and Canale. The edition I have is 7th edition, but any recent edition is okay. Better yet, go online, this site, and find this free online textbook. It's very well written. It just doesn't have nice colored pictures and glossy stuff. Since you have been using numerical calculators for long, and you will learn today or in this course numerical methods, there is another thing that you should become familiar with: symbolic calculators. So there is a program called Maxima. You can download it. Again, it is a freeware. It is available on many operating systems, even on your cell phone, probably depending on the OS you use. But it's a very nice way to check on your work, even in other courses. So try it out. It's an excellent symbolic calculator. If you need any help, make an appointment with me and I'll be happy to help you get started. Okay, the instruction is online asynchronous for this course, for this semester. Now you will see in my schedule, I do want to meet with you 4 or 5 times. We'll talk about that in a little later on. So our semester is made up of 14 instructional weeks and a final exam period. Each week is 2 lectures and a lab, each 50 minutes. Each week runs Monday through Friday. So we are going to have lectures on Mondays and Wednesdays. I'm going to post videos for each day. They will be numbered. You will have them posted by 8 a.m. in the morning. So you should be able to watch them at 1 o'clock class time if you're maintaining that kind of a schedule. Labs would be on Fridays. Uh, as you will see, I just spoke. I have a lab teaching assistant, Anthony Lord, and he is going to maintain that lab section time spot on Fridays as office hour. Since the instruction is asynchronous, please develop your own routine to review the slides and videos. I would strongly suggest, if this 1:30 to 2:30 time, Monday, Wednesday, Friday, suits you, it should, since you're signed up for the course, set it aside to watch the videos, and I'm providing you the accompanying slides. I hope to have it loaded by 8 a.m. each Monday for the entire week, but at least for that day, you will have it ready by 8 a.m. To get a big picture of the course, the best way to look at is grading. So after every lecture, you're going to have an online quiz. So there are going to be 22 in all, 1% each. So that's 22%. Each week, you will have to submit a lab. That's 2% each. You'll have 12 labs in the whole semester. That's 24. Uh, I'm going to have 2 midterm surveys. These are just going to be online surveys, 1% each. Since it is course is asynchronous, I really want to know how things are going. So I will show you in the schedule when these surveys would be. And then, of course, we are going to have 2 midterm tests, 17% each, and a comprehensive final exam, 18%. When I used to teach in person, I did not need these surveys because I would meet students every week, 3 times at least, and I could get a sense of how things are going. So I borrowed 1% for these midterm surveys because our course is online. Course grade, in my courses, usually people do extremely well. So usually I don't have to use a relative grade. So it is strictly 90 and above A, 80 and above B, and 70 and above C, so on and so forth. But if some for reason class is not doing well, I will use this kind of a relative criteria. Note, I give whole grades. I don't use the plus minus grading system. I know for a particular case, for a particular individual, sometimes the whole grade may not be very good, but for the aggregate student body, my statistics tell me that whole grades are much better than plus minus grading system. So I'm going to use whole grades. So here is the tentative schedule. Tentative in the sense that on some days I may be running a little slower, so I may spill over to the next class. There might be a few days, very few, where I might be running a little ahead, so I might borrow from the following week. But other than that, I'm going to stick pretty much to the schedule. So you will see each week is marked by these double line borders. So we have 14 weeks. Uh, Friday of each week, we have a lab. Now, the first day of class, I would like to meet with you synchronous using Zoom. So we can say hello and hi. But here is a video. I'm not going to go over this video, um, but just to chat. And then in sixth week, we are going to have a review for the midterm. So there, of course, you can ask me questions during this Zoom session, and I will be happy to answer you. Then again in 11th week, we are going to have again a review, and I would like to have that as a Zoom session. Note that there is the survey here in 6th week. There is a survey here in 11th week. And then again, we'll have a review for our final. And I have this filler space here, and maybe we can chat again using Zoom to see how we can make the course better. Okay, here is the online quiz after each class, 10 multiple choice questions. Usually you'll have 4 choices. You will have 3 attempts. I'll count the best of the 3 attempts. It is due by 1 p.m. of the next lecture class. The reason this is remember, I want you to maintain a 1:30 to 2:30 schedule so that you don't get behind. I'm going to post the answers by 11 p.m. of the due date. Test questions would be same or similar to these. So here is what I suggest about online quizzes. Start the online quiz the same day. That means at least review the questions. You may even answer, but you do not need to submit your attempt 1 until you are ready. This way you will have reviewed what the questions are, what are the key ideas, and you can review the video or the slides of that day. As you start working on the questions, record your work in a notebook so you can go back and see if you could have made a mistake. Please do not guess the answers. So the whole idea of the quiz is you should, if you really think you understood the material, you should score 10 out of 10 without any problem. But let's say on attempt number 1, you score less, equal to or less than 7, then seriously, I think you really need to review the lecture slides again, if not the video entirely. To figure out where you could have gone wrong, try resolving the classroom examples on your own. In my videos, I will encourage you to calculate along with me, but some of you may not. And probably that is one of the problems you are having. So try resolving the classroom examples on your own. Then on attempt 2, if your score is less than 9, you really need to find out what is not clear to you, which of the 10 ideas. Of course, when you submit your attempt, you will just get an overall score. I'm not going to tell you which questions you have wrong. You have to figure that out on your own. That is the whole idea. You need to figure out what you really understood and what you have not understood. And you should be able to look at your work that you have done in your notebook and figure out which question you had wrong. In student surveys, I've had one of these issues. On some quizzes, you'll find a sequence of questions that appear related. Yes, they are related in the sense they are different parts of one problem that you are investigating. You can treat each of those problems as a standalone problem. So there is no reason why you need to think that they are related and complain when you don't score well. Uh, Visit me earlier in the semester if you are not understanding the material. I'll be happy to help you. I have many other ways to help you. Uh, but do contact me. When you are preparing for test, review the online quizzes. You will have answers available to them, so you should be able to uh, prepare for the test. For the weekly labs, for each week, go to the lab slides and have the lab template ready and open before you begin seeing the video, so you can follow along the video. Now, on my slides, I do have step-by-step instructions. And some students have said in their surveys that they are really not necessary. But on the other hand, there are many students that find them very helpful, students who are not fluent with Excel. Upload your lab macro-enabled Excel file to the Dropbox by 11 p.m. This is a key problem. Many people do not submit their macro-enabled files, so we cannot see their macros and we cannot activate the macros. So please make sure you submit a macro-enabled file. Yes, I have my fixed template. I have these very fixed steps. If you find a better way to solve a problem in Excel, let me know, and I'll be happy to incorporate it in my class. Um, so I really would appreciate if you can tell me if there was a better way I could have done a particular Excel implementation. I will have 2 midterm surveys. You're welcome to provide suggestions and criticisms to improve the course at any time. You don't need to wait. There is a slide. This should be week 6 and 11, I meant. Week 5, I get them ready. I'll post them. So a midterm survey will be administered. Each survey will consist of 10 multiple choice questions and is worth 1% of the grade. So I really am interested in your views. Few of the students in the last couple of semesters wrote that they were not, they did not find labs challenging enough. So for those of you who want to work with some challenging problem, they're not really very challenging. It's just that you have to model them. So I'm going to assign one modeling problem every week. It's optional. You don't need to work on it, but you may see how this course applies to engineering problems. Please model and formulate the problem. So let's suppose you do a derivation, capture that derivation, figures and all, in an image that you can include as a separate worksheet in your Excel submission. So you can use the Excel spreadsheet that you have developed for that week's lab and solve this optional modeling problem. Please upload in a complete solution to the Dropbox by 11 p.m. of the lab due date. This would be graded by me. Grading would be pass or fail. You really want to submit a decent problem. You don't want me wasting time unnecessarily because remember, this is optional. But I'll be happy to talk to you if you want to. Okay. Okay, what is the course all about? So, numerical method is basically a method to solve approximately a mathematical problem. So what does it mean? solution is numerical. So it is in a number form. So suppose you are looking for A, it does not say A is equal to pi cube over 6. It says instead A is 1.45 whatever. Solution is approximate, so it is not exact. And method is basically repeatedly applying a sequence of one or more steps to solve the problem. That's how we keep approximating something. Any mathematical problem can eventually be reduced to solving one or more equations. So that is what we are going to learn, how to solve one or more equations. Since we are interested in getting unique answers, we'll restrict our course to solving always n unique equations in n unknowns. That way we will have a unique solution. What kind of equations? Well, equations could be of any kind. They can be algebraic equations, simply like x squared plus sine of x minus e to the power x is equal to 0, and we want to solve for x. So in general, we can write that equation as something in x is equal to 0, solve for x. We could solve an integral or evaluate an integral. So we could be given an integral of this form. Or we could be given a differential equation and we could be asked to solve a differential equation. So we'll take each of these kind of equations, and there can be many more. But the key idea is all these equations we would be able to eventually reduce to a number of algebraic equations. Now, where do these equations come from? Well, let's say you have an engineering problem that you want to solve. Well, typically engineering problem is quite complex. So what we do is we make assumptions, we simplify the problem, we create an engineering model. So we take the engineering problem, we model it, and we convert it into a mathematical problem. Often the mathematical problem is simple, so you don't need to do much further. You use things that you have learned in your Calc 1, 2 classes, algebra classes, and you can solve it. But real engineering problems, often the mathematical problem that it results in are maybe too complex to be able to solve with pencil and paper. Maybe they do not have an exact solution, in which case we use a numerical method to solve this problem and we get a numerical solution. Once we get the numerical solution, remember it is an approximate solution. So what we want to do, even if it was an exact solution, always you should verify. Is this really the solution to your original problem or not? Once you have verified it, the next thing, of course, as any engineer would do, you need to make sure that this solution is still meaningful to your original engineering problem, and that's called validation. So obviously, if we screwed up somewhere in this loop, we would not be able to verify our solution. And of course, if we screwed up in this loop, engineering modeling loop, then this would not be a valid solution to our original engineering problem. So therefore, in solving an engineering problem, we have 4 major steps. So given a problem, we first create a model, then we formulate it, and then once we have a formulation, we solve it. And once we solve it, we want to always verify and validate. So these are the sequence in which we go: model, formulate, solve, verify, validate. So where do we get these one or more equations? When we have more equations, we say we have system of equations. So we'll say we have a system of 5 equations or 3 equations. So in numerical method, whatever kind of equation we have, first it does is it converts it to a transcendental or algebraic equation. And then it solves. If we had one equation resulting in one equation, we solve one equation or five equations or whatever. So what is a transcendental equation? A transcendental equation involves transcendental functions, transcendental numbers, such as sine x, cosine x, all these trigonometric functions are transcendental functions. Exponents, any x raised to a real power, this real power is a transcendental function. And then we have a subset of this equations called algebraic equations, like a polynomial. So a polynomial is where x is always raised to a integer power, 0 or more, positive integer. So in this course, we are going to learn to solve one or more equations. So we'll begin with one transcendental equation. Then we are going to look at one polynomial equation. Of course, one linear algebraic equation is easy to solve. We know A, we know B, we can easily find X. But formally, that is what one equation is. So obviously, we can have n of these equations. So we will learn how to solve a system of n equations. So we will know A, we will know B, we will like to find X. Same way, like here we have one equation and one unknown. So here we have one function equal to 0. A system of equations will have n functions equal to 0 in n of these unknown x's. So we'll learn how to solve those. So when we say we are getting approximate numerical solution, what do we mean by that? It turns out most of the computing machines that we use are really limited precision devices. That means they are approximating machines. They do not calculate exactly. So even if we had an exact method we use with these limited precision machines, we'll always get an approximate solution. And of course, if we don't have an exact method, if we have an approximating or an iterative method, it doesn't matter whether we have an exact computer or we have the usual limited precision computing device. Of course, we are going to get an approximate numerical solution. So most of the times, once we involve computing devices, we are always getting an approximate numerical solution. So the key question is how approximate it is. So we are concerned about words such as precision. So when we say approximately, the answer is 5. Obviously, you should ask how approximate is this answer. So somebody should give you an answer. Is 5 plus minus 1 or 5 plus minus 0.5 or whatever. So obviously we cannot tell the exact error, but we should be able to put a bound on the error. So we should be able to say how large can the error be in our approximation. So of course, we are using a method to get this approximation. So we are also interested in convergence. Will the method find the approximate solution? Will it converge? So there may be certain conditions when it would or it would not. We are also interested in efficiency. How much computer time will the method take to find a solution? So some methods may be better than others for a given problem. So we would like to know, therefore, efficiency of a method. And then finally, we are also interested in stability. In an iterative method where we do calculations repeatedly, we really would like to know, are the errors becoming progressively worse so that eventually the solution even doesn't make any sense? Or are the errors remaining relatively stable, controllable? So in previous calc courses, you have learned what are called analytical methods. So Let's compare numerical to analytical method. So the great thing about analytical method is it forms a closed form or what is called an exact solution of an equation. So that's the positive part. The negative part of it is you can only solve a very limited types of equations. A vast majority of the equations you cannot solve analytically. So in many cases, it is impossible to say whether an analytical solution exists. So if somebody gives you one equation or a set of equations, just by looking at it, you cannot say if a solution exists. You have to work. You have to work with the problem to find if a solution exists or not. Now, you can use computer algebra systems such as Mathematica Maple to find analytical solutions, but they are computationally expensive, especially for complicated problems. Well, a numerical method provides only an approximate solution, not an exact solution. So this is kind of a negative. However, you can solve unlimited type of equations. So this is the biggest thing about numerical methods. In many cases, it will be impossible for us to determine if our numerical method will converge to the solution or not without trying it. So often we have to try it. However, numerical method is computationally very inexpensive. So really, it does not cost us very much to try it, even if it may not converge. But if it finds the solution, we have got a very inexpensive solution. Now, in teaching the course, whenever I'm covering any numerical method, I'm going to use three formats. I'm going to explain the method symbolically or algebraically. I'm going to explain the method showing a graphical format, and we will do a number example. Now, I may not do them exactly in this order. The order might change depending on the topic, but I hope to explain to you the method in all three forms. We are going to use a number of words. So let us see if we can develop a certain nomenclature. So often we are interested in finding the unknowns, value of the unknowns. So typically we say unknowns are X, Y, Z. But really, once we have many unknowns, we would like to number them. So we number them X1, X2, X3. And these are the unknowns whose value we want to find. Then there is something called parameter. So often in our equations, we might have variables such as alpha, beta, gamma, whose value we don't want to find. We may just need to change it. We may need to vary it within a known range, but we know what the value should be or what we want it to be within this known range. And then, of course, in our equations, we may have constants. Typically, we use symbols such as C1, C2, whose value we know definitely, but we don't want to list those values just to clutter up those equations. Okay, let's look at a real life engineering modeling example. Let's suppose we have a cylindrical trough of some liquid, water, let's say. And imagine as if it is lying on the ground. So that means this is our ground surface, and this cylinder is coming out of the board. So we want to know what is the water fill ratio. That means this ratio of height to radius given a certain fraction of this trough is filled with liquid. So let's suppose we say if this is 20% filled, what is the H over R ratio? So as we try to model it, let's try to find what is the volume of the water. So the volume of the water is going to be this area, times the length of the cylinder. So if we look at the area of this particular portion of the circle under this chord, it turns out, you can look up a handbook, to be this term in square bracket. So this area times length is the amount of water in the tank. And of course, we know the volume of the tank is going to be the total area, which is pi r square, times the length of the container. So if the percent water in this container is alpha, fraction of water, then we will divide this first equation by the second equation, and we will get this particular quantity. So in this particular quantity, if we define H by R as X, we can write this entire right-hand side only in terms of X. Of course, there'll be constant like pi involved, function involved. So if we take this pi to the other side, we will have pi times alpha. So this bracketed term minus pi alpha is 0. So this whole left-hand side, we say, is a function of x, because we know everything here except x. So in this equation, if we are given a value of alpha, let's say 0.2, 20% full, we want to find out what is the fill ratio, x. So obviously you can see right away, looking at this equation, it cannot be solved algebraically. So we need to solve it numerically. So this is what we mean by one transcendental equation in one unknown x. So if you go back, we have this equation. If we knew the value of alpha or given the value of alpha, alpha is a parameter. So this is a parametric equation. But given the value of alpha, the only unknown is x. This equation involves trigonometric functions. It involves square root. These are all transcendental functions. So we have a transcendental equation. So we have one transcendental equation in one unknown x, and we can always write it in this form. F of x is equal to 0. The value of x that satisfies this equation is called a solution. So x is solution of this equation. We also call x as the root of this function. So solution of an equation or root of this function means essentially the same thing. Now it may turn out that this may not have any real root, in which case a real solution does not exist. Or this function may have one or more real roots, in which case this equation has many solutions, or the function has more than one root. So the question is, why should we use numerical method to solve this equation? So as we just saw, the function may have no analytical solution. We just looked at this very, very simple problem, and this has no analytical solution. Or analytical solution may be too difficult or time consuming. I just said numerical methods are inexpensive, they are cheap, it means they are easy to use and do not take much computer time. Also notice, if we do not know this function explicitly, that means it is embedded in a black box, like in a hardware or software system. All we can do is, this is a black box, we feed it x, it tells us what the function value is, in which case we can do nothing analytically. So we have to use numerical methods. So let's see, what does root of a function mean graphically? So what we do is we plot the function. So here is our x-axis. Here is our function, and we plot our curve. And let's suppose this curve looks something like this. It never touches the x-axis. Since it never touches the x-axis, fx is never 0. So this has no roots. We are always talking about real roots in this course, unless it is specified in the problem. Let's consider another case. Let's suppose the curve looks like this. Now it touches the x-axis here. So here fx is equal to 0. So since it touches the x-axis only at one place, we have one unique root. Let's consider another curve, this one. Here the curve touches x-axis at these two black spots, so two distinct roots. Here it touches three places, three distinct roots. So let's take a look at a very simple problem. We want to find square root of a. And here is a very interesting thing. How does your calculator square root key work? You ever wondered? Obviously, your calculator is not storing square root of all possible values. That would be infinite. So how does your calculator work? Well, it uses a form of numerical method that you're going to learn here in this course. So let's say we want to find x is equal to square root of a. We want to solve this equation. We are given a, we want to find x, and let's also suppose we are only interested in positive root. We know that it has two roots, positive and negative. We are only interested in positive root. So if we square both sides, it implies x square is equal to a. So if we move a to this left hand side, we will have an equation of the form x square minus a is equal to 0. So the function whose root we want to find is this function x square minus a. Now we know that the positive root of this function lies between 1 and a. So let's suppose a was 5. Square root of 5 would be between 1 and 5. So in our example, we'll assume a is equal to 5. So we'll try to find square root of 5. Well, one way we can just do, we just looked at how to find root of a function, we plot it. So we could use plotting method. Well, plotting is really not a numerical method. We would need to know the range of x for plotting. Well, in our case, we know the root of 5 is between 1 and 5. So we can plot it between 1 and 5. But if we didn't know that, then we may need to experiment with different ranges. So we will select a range AB that contains the desired single root. So if our function has many roots, we will say we want this particular root. So if we do so, notice our situation would be like this. We have one single root. We want to plot the function, let's say between this range. So this is A, this is B. So notice when we take the function, since our curve will cross the x-axis, if it crosses the x-axis, it need not cross to touch it. But if it crosses the x-axis, function at A and function at B would have different signs. Here it is negative, here it is positive. It could be other way around. But that means that f times A, fa times fb will be less than 0. These are going to be two opposite signs. So in the first lab, what you're going to do is you're going to learn how to create a spreadsheet to plot a function within a range, and you're going to plot the function to find where it touches the x-axis. So in part of this, once you have created a spreadsheet, what you're going to do is you're going to put the function in a VBA function, a Visual Basic Function. So what would happen is, once you have learned how to even plot a simple function like x squared minus 5 in our case, later on, if you wanted more complicated functions such as what we had with the cylindrical trough, we can put in all that cosine, minus, inverse, all that pi and all that here in our VBA function. And then as soon as we change the function, our spreadsheet should change and we should be able to change different ranges to find our desired root if one exists. So this is what you're going to do in the first part of Lab 1. Learn how to create a spreadsheet with a VBA function so that you can plot any function in any range that you want. Okay, then we are going to learn real numerical methods to find root of function f of x. So there are two categories of methods: bracketing methods. Bracketing methods are such that we are always bracketing the root, so they are always guaranteed to converge. And there are many such methods. We are going to cover only the first one, bisection method. But as we discuss these methods, I'm going to mention what linear interpolation method is and what other methods might be. Then the second category of methods that we are going to talk about are non-bracketing methods. Non-bracketing methods may not always converge. However, they may have certain other benefits. So we are going to cover three such methods: secant method, Newton-Raphson method, and fixed iteration method. Now these are all iterative methods. So iterative methods are of the form, what we do is we have an unknown that we want to find. It may be more than one unknown, but let's say we have one unknown. So what we do is we begin with a guess. Let's say we want to find x, so we begin with a guess. We'll call it old x value. Then what the method does is it allows us to compute some refinement based on some logic. So let's say that refinement is delta x, which improves the guess. So now we have a new value from old value plus the refinement. Now, if the refinement is very, very small, that means really we are not improving the new value much from the old value, which is what we call the convergence criteria. Then we stop and say, hey, this is a good enough approximation to our answer. Otherwise, we keep repeating steps 2, 3, and 4, of course. We keep computing newer and newer refinement till we have converged, if the method works. So that's the basic idea that we are going to be using throughout the course. And the first method that we are going to learn is bisection method in our next class.